Ok. Hay que darle que sí, ¿no? Hay que aceptar. Hola, buenas tardes y buenas tardes a los de Ensenada. Esperamos unos minutos más y comenzamos. Yo creo que podemos empezar.
Sí, Daniel, ya vamos a empezar. Muéstrales las fotos. Bueno, después.
Ah, es que es...
Sí. Pero tú, mira, ¿no? Tú dales la bienvenida a todos. Buenas tardes a todos. Es un gusto para mí presentar al profesor Daniel Kunth. Daniel es un viejo amigo. Ha hecho muchísimas cosas. Una de ellas, él es uno de los instigadores de la Noche de las Estrellas en Francia. En 1991 la inició y nosotros la hemos tomado aquí en México. Y bueno, Daniel tiene una carrera bastante interesante, multifacética. Él hizo su doctorado con Walt Sargent en Caltech y trabajó en un tema muy cercano al corazón de Manuel, en helio primordial. Daniel trabajó un poco después de que Manuel presentó sus primeros trabajos, y de más o menos de entonces a la fecha creo que no han avanzado mucho más en los detallitos, ¿no? Y Daniel posteriormente ha trabajado en diferentes temas. Él fue de las primeras personas en reconocer la población de estrellas Wolf-Rayet en galaxias enanas, y recientemente ha estado trabajando en la emisión de Lyman alfa de galaxias. Él fue de los primeros en trabajar en esta parte, y con un grupo grande de colaboradores, un grupo más o menos informal en varios lugares del mundo, ha estado trabajando en la emisión de Lyman alfa en diferentes galaxias a lo largo de las diferentes épocas de evolución del universo. Entonces, Daniel, bienvenido. The floor is yours.
Gracias.
There you have microphone there. Va a dar su charla en inglés.
Sí, bueno, muchas gracias.
Ahora sí.
Bueno, entonces.
Descubriste tu voz.
Sí.
Like the kids, whenever they start,
Exactly. Sí, un poco, ¿no? Así es. Entonces es un placer realmente de encontrar a ellos aquí y descubrir este lugar que realmente nos sorprende mucho. Hay muchos institutos, muchas personas, es realmente un sitio increíble, interesante, entretenido. No voy a seguir en castellano porque se da cuenta que muchos de las palabras son inglés y que yo tengo que traducir un poco complicado. Entonces, disculpe, pero voy a continuar en inglés. I hope it will be better. So today I will speak about Lyman alpha emission. Lyman alpha emission first from nearby galaxies, and then extend this study to distant universe, to distant galaxies, and touch a little bit to the problem of reionisation of the universe, because now it is supposed that the actor who plays the role of reionizing the universe between 6 and 7 is most probably a dwarf galaxy. So that's why the dwarf galaxies, emission galaxies producing Lyman alpha, are playing a very interesting papel in this game. So why do I say, so I am myself working at the Institut d'Astrophysique de Paris, in Paris, but LARS means Lyman alpha reference sample, because when we started I started this game in 91 by obtaining the first Lyman alpha images of galaxies using HST and using the advanced camera, ADS. And then we were very surprised from what we obtained. It was a very, very little number of galaxies at that time. And the Lyman alpha behave in ways that we had to analyze very well. And we decided to build a reference sample with more than 45 galaxies in order to work out all the parameters, many, many parameters that contribute to the escape of Lyman alpha. And this is why Lars is the name, and also because Lars is a nickname for Swedish people, Lars von Trier, you may know, and also because when I started this, I started to collaborate with Johan Oslin from Stockholm Observatory, And he came back. He came to Paris for about 2 years. We started this project. He went back, to Stockholm and started to have many students. And we collaborated with many other people in Spain with Miguel Mas, who else? In Geneva with Daniel Scherer and Veram. So this is about a group of more than 20 people, 25 people, plus some people in Mexico. So I remember having worked with you here. And so that's what I am going to present here. It's not only my work, it's the work of a group centered on the last of a galaxy. So now I have to touch this properly. You say slow, but is it there? No. You said here.
And now? Okay.
Where did you put?
Here.
Yeah, I did too, but okay. So this is, of course, you recognize this nebula, and from this nebula, because you have gas and you have very massive stars, you produce ionized gas plus emission lines. On one of them, Lyman alpha is unique because it should be, in principle, the brightest emission line. It should be in principle. It is expected that the ratio between H alpha and Lyman alpha under conditions which are prevalent in this nebula is about 10. Okay. But of course, the Lyman alpha is in the UV, and it was extremely difficult for a long time to observe this line. But interestingly, when quasars were discovered, they were discovered because they had some redshift, and the Lyman alpha from quasars were first observed. And at that time, Partridge and Peebles discussed the possibility to identify young galaxies by observing Lyman alpha as a proxy. They thought that because so they produce, in fact, the slope of what should be Lyman alpha line, and they propose that Lyman alpha emission would be a very strong part of the flux of the entire ionizing continuum. So of course, there were then many investigations on. First, there was IUE. This was a very small telescope, which was able to identify one galaxy. That was the work from Meyer and Terlevich, and they found a very strong emission line in one of the galaxies they observed. But that was only one case, and this satellite was a very small one. So people started to initiate surveys from the ground, and most of them were very unsuccessful. For many reasons, because sensitivity, and mostly because the line strength was much below what was expected, what the recombination values would expect. And then came, of course, the CCDs, and using narrow filters, it was possible in some cases to identify some of the first, what we call Lyman alpha emitter, and at that time, Taniguchi, for instance, produced this result. You know, you set up in one part of the sky, and you use different filters. You see nothing. Here you see a continuum. Here you have a narrow filter, and you see a very prominent signature, and that was, you know, above the continuum signal, and this was the first example at that time, one of the first examples of a Lyman alpha emitter. This is one thing, okay? Now, in fact, what about local objects? To get local objects, to be able to do it, of course, you had to have satellites. And as I said, IUE was not designed for that, and very small. And indeed, with the advent of VHST, that it was possible to do high-resolution spectroscopy on high-resolution imaging from nearby galaxies. Okay, and we did that. We, of course, first targeted to 15018, which is Markarian 116. I don't think it's an Haro object, but we will come back to that. And we expected very strong emission, and instead, we found this is a spectrum obtained with HST, and we found absorption lines, no emission lines. On the other hand, using Haro 2, which is a very nearby galaxy, we found absorption and emission, a P-Cygni profile. Okay? And it was rather puzzling at the time because we thought, well, here is a galaxy which is rather dusty, not extremely dusty, but it's rather dusty, whereas the other one is not. 15018 was still one of the most metal-poor galaxy, and it's on this one that you see emission. So we understood that that the puzzle was going to start and not finished, even now, but there is more than one parameter that drives the visibility of the Lyman alpha. And the main reason, of course, that most spectroscopists could understand and guess is that the Lyman alpha is a resonant line. So when you produce the Lyman alpha from, when you produce this emission from in a ionized medium from a source, which could be one of the most massive stars that you have in the cluster, well, of course, the line can be either destroyed by dust or is absorbed, re-emitted in different directions and so on. So if you have a lot of dust, if you have a lot of H1, a lot of gas, the chance that on the line of sight, you will not necessarily produce an emission, but an absorption. And if you have dust, then the dust will destroy Lyman alpha immediately. And this is not the same for H alpha. H alpha, of course, doesn't come from the same atomic level. And he looks at H1 as a transparent medium, and you can see it. This is the main region. And that was in 1991, 93 with Lugar, with Terlevich, with other people, Miguel Mas. We observe only a hand-picked sample, 8 galaxies. And you see Haro 2 that I showed before, and some were IRAS, so it's rather dusty, ISO galaxy 15018, Markarian 36. And so you see the list, some were in absorption, and some were in emission. And this is a second part of the spectrum, because it was the GHRS, which only covers a very small spectral range at the time. So we had two settings. And in this side, we were looking at absorption lines. And we could see that when you have such a thing, the emission and the absorption, the metal lines, in fact, show that the medium is moving with respect to the source. This is why you have an emission, a P-Cygni, whereas here, the absorption, the metal lines absorption is at the same radial velocity than the galaxy. So in this case, you always have an absorption or nothing. So that was the main result at that time, but only on 8 galaxies, showing that the dust is an important consideration, but also the kinematic of the interstellar medium. Okay. So we had 2 parameters, but not the only one. So at this stage, so this is what I basically said, but it's an enlargement of the things. So at that time, we were thinking how to explain, because all the 8 galaxies were starbursts. Okay, so it seems to us at that time that a starburst alone doesn't guarantee to have a Lyman emission. So you had to understand that. On Tenorio Tagle and ourselves, we work out a model by which you have a starburst, you have a surrounding medium, you have supernova, you create a bubble, hot gas and emission lines produce this situation. And then, of course, you have, because of the dynamics, you could have a P-Cygni profile. And then at the end, when you accumulate gas, which is going to cool again on being neutral, you can obtain a situation in which you have an absorption lines. So that's a very schematic on a movie, if you wish, but that was in 2000 only. Now, then we got images of these galaxies, these 8 galaxies. And then I show you early imaging. That was in 1998. And these images were obtained with the ACS camera. And it shows very important result, which has been proved even for distant galaxies. Of course, the colors are coding H alpha, Lyman alpha, and oxygen free here. And you superpose the image. And what you see here in the blue is the Lyman alpha. Okay? And so the effect of dust is not, I don't want to enter all the details, but what I want you to look at is, for instance, this galaxy. You don't see it very well, but the blue is very extended. The blue is Lyman alpha. So it shows you that the Lyman alpha photons are diffusing, scattered in the medium, while most of the emission lines produced by the stars, even H alpha is not diffused, so it's much more connected with the source of emission. Okay, this is another example. I see much better on my screen, by the way. So that's where we decided to enlarge that and to obtain more and more galaxies, and we started to call this project LARS. That means Lyman alpha reference sample. Okay. And it took us many years, of course. The sample selection, we tried to have a statistic, so the sample selection was taken from GALEX and from SDSS, and it was, we wanted the H alpha equivalent width to be larger than 90 angstroms to ensure that we were dealing with starburst galaxies. And then we had about 20 objects, and then we enlarged the criterion by adding galaxies that were less strong in terms of starburst. So we put a lower value for the requirement for H alpha. So in total, we have about 45 galaxies, which is not too bad, but it's still, we would prefer to have 2,000. That's it. And the observations were done with HST, and we were using different filters, combine the filters in order to minimize yeah, because we could use a narrow filter for Lyman alpha, but the emissivity was not so good, efficiency was not so good, so it was much better to use all these broadband and superimpose the image in order to cut the region of interest. And then we had also some broadband filter, and we use the template starburst 99 with parameters. We could obtain emission lines. We could work out the history of the object, and focusing, of course, on the Lyman alpha. And now I show you briefly, quickly, because 45, I'm not going to analyze, but to show what happens. Would be better to come here, because here you see very well the blue. For instance, here there is a huge blue image, you know. So it was really very fascinating to see the ability to observe and to pinpoint the diffusion, which is due to the resonance properties of Lyman alpha. And so you see there are a lot of different shapes. For instance, here, you see that because the orientation is not the same, you have more porosity, you have, of course, the Lyman alpha is going through a different part of the galaxy and encounters less or more H1, so that makes the difference from one object to the next. You see it better here. Thank you.
What's the difference between the left side and the right side images?
The left side is the visible one, okay? On the right side is the one in which Lyman alpha filter is going to be more visible. So we can identify Lyman alpha visible here. Here you see red images, you can see the dust better, and so on. So these are the galaxies. So there are many on different kinds, and so we could, since we are about 20 who have been working on that, people have been looking at the distribution of the dust, distribution of Lyman alpha, where you have H alpha, with the ability to measure the ratio, to measure the dust, identify where star formation is. Yeah, for instance, this one is very specular, very, very particular, where you see Lyman alpha corona. Okay. Since I have not my laptop with me, I was not able to get rid of some of the slides, so I will do it just now on the spot. But you see, this is one object, which is Haro 11. I will come back to Haro 11 not because it's Haro object, but because it's a very important one for our purpose at least. You know, here, for instance, you see that for the same object, the Lyman alpha image doesn't resemble the H alpha one. Doesn't resemble. Okay, so it's not astrophysics; it's physics. It's a transfer problem. Okay, and but this is a clear evidence for the resonance scattering of the Lyman photons. Yeah, here you see it. You see it another way. You have 3 knots in Haro 11, and all what is blue here is not noise. This is Lyman alpha. So this is a clear, I think, a clear image in which you see H alpha. This is there is very little dust in this, but I will come back at the very end of this. So the question then is, how do we know that Lyman alpha will escape or not? So this plot has been produced by my students, kinematics, showing that in fact, all these points are galaxies, different studies, not only our study, but you have Scarlata, Cowie, IUE sample, and you show that what we call the fraction of Lyman alpha photons that escape is called F escape for the Lyman alpha photon. How do we do that? Well, we know that if you have H alpha, H beta, you know the dust, okay? And you can correct for the dust. And we have the observed Lyman alpha, the observed H alpha, so we can compare with what is expected. And from the difference between the expectation and between what is observed, you obtain the fraction of Lyman alpha that eventually escape from the galaxy. And we call it F escape. And this is the dust which is measured by many methods, but H alpha to H beta is one. And you see that the dust is playing a role. But there is a very large dispersion around this. And the dispersion is larger than, well, sometimes it is accounted by the errors, but if you see at a given dust value, B minus V value, there is quite a very huge scatter. So this is why we think that there are many more parameters that are active in this game. Okay? I skip that one, but nevertheless, if you can, so the idea was, are we able to find a relationship that from the Lyman alpha, you can measure the star formation rate? Because if you want to measure the star formation rate of a universe at a given redshift, if you use Lyman alpha, you are not sure that you get the global star formation rate, because some are absorption, some are emitters, and some do not show up in emission. And so we have made this comparison between the H alpha star formation rate we get and here, and the one we get from the Lyman alpha after we have made all this correction, and we get some fit, but just a fair calibration with significant scatter. So the result of this is that Lyman alpha is emitted on scales that exceed the one of massive stellar population, on the one of the recombination nebula. There is an overall correlation with dust, of course, but the simple dust correction is not enough to correct the star formation rate, because there are other parameters: porosity of a galaxy, inclination of a galaxy, density of a gas, kinematic of a gas, and so on. So there are many mechanisms. So unfortunately, it's a poor indicator, but it's an indicator. Okay? And we see, of course, we have this diffuse halo. This is a firm evidence. And the escape fraction, most of the time, is low. Is less than 10%. So it's very easy to kill the Lyman alpha photon. So this is, now for your archive, this will be public. You have a paper which is published here, and another one by Erens, which is also has been done by PIMAS, which is going to be accepted, nearly accepted now. And all of that will be released to the community in MAST. Okay. Now, in the meantime, of course, people observe the large, the distant universe, and you know that they're using MUs, stacking spectra on images. It was a Seidel discovered independently that, in fact, very bright halos are found around high redshift Lyman alpha emitters. Okay? So, the difference, of course, is that you don't see the object, you see only something like that, very spherical, and you have no detail where exactly it has been produced. So this is, I think I will, yes, yeah. So another interesting point that we discovered, my student Hakim and myself and other people, was that there is, in fact, if you, on Hayes is part of the team. Hayes, Cannon, Melinda, Terence, have not put all the names, but we are about 20. Not always, but about 20. And this function shows that with redshift, the escape of Lyman alpha is a function of redshift, increases with time. Okay? This is a combination of many other work, not only our work. This OU is Uchi, Japanese. And what about Lyman alpha emitters? We show also that the luminosity function evolves with redshift in terms of normalization and shape. Okay, and at 5, okay, where we think we start to enter in the ionization era. Okay, that's probably the reason why there is this very strong evolution of luminosity function. And many people found, well, we won't find Lyman alpha emitters beyond 7. Beyond 5, and in fact, it's not true. We still find, but of course, they are rare, as the QSOs. And to show you the very tricky point here, is that we found Lyman alpha, we found high redshift galaxies, which at Z equal 2, it's not very high, but about 1.9, 1.93. And we had a spectrum from a spectroscopic follow-up by Keck, with Keck, 2 dwarf galaxies, okay? So what we found was that, okay? You start with nearly the same, both galaxies at about the same spectrum to start with, okay? So you would say, well, both because they are high ionization galaxies, you know, this is 507, 49, 59, so oxygen lines. So it's rather high excitation. So you would expect, because it's higher excitation, to see the Lyman alpha. Now in this case, you see it very well. In this case, no. No. So you have to deal with nature, my dear. So that's a funny situation. Now, if you want to go, you have a sample with Lyman alpha emission. Can you ensure that with that, you will be able to find the Lyman continuum emitters? Because what we are interested in is to know whether these galaxies that produce strong starbursts are able also to produce continuum to ionize the gas. And so you can see, so you can compare Lyman alpha emitters on LBG galaxies, okay? And it's not so clear. It is, yes, Lyman alpha, you see it is when it is expanding, and this increases also when you have strong winds. Okay, so if you have expanding wings, you can expect to have a continuum, or Lyman alpha continuum as well. This is Lyman alpha, this is Lyman continuum. Okay, porosity, of course, we cannot easily measure that. So this was I think I will skip that very quickly to show you this video. Now, galactic outflows is something interesting because you can see that if you have a large outflow, of course, this is the center of Lyman alpha, and you can scatter the photons in the red and in the blue. And in this case, which is that one here, where you have, in this case, you expect to have possibility for Lyman continuum to escape. So people were trying to find out Lyman continuum from galaxies in which Lyman alpha was not symmetrical, but produced 2 different bumps. I will go, yeah, I will skip with that. And voilà. On very few galaxies are known to be Lyman continuum emitters. The first one was found using FUSE, a small satellite that you heard about, and on few others, and they seem to be a very fairly good correlation, I don't know if I can say that, between Lyman alpha and Lyman continuum. Okay. The first one was found with FUSE, as I said, with Isotov on his group. Very difficult to get. And then models were produced to show that there should be a model showing that if you know the peak separation in Lyman alpha, you expect to see, in fact, it's a function of the density of the medium. And in this case, Isotov has shown that, in fact, this is the fraction Lyman continuum fraction escape as a function of the velocity separation of the outflow. Now, I just finished with, with two things. One is the study of Haro 2, Haro 11. And then I will show you the very last result obtained using JWST. Okay? And showing that now we believe that the dwarf galaxies are responsible for reionisation. But start with this one. This one is, Haro 2 is this one. Okay, it's very similar to antenna in terms of morphology and star formation. And this thing, what does it do? Yeah. So what you see here, yeah, okay, no. How can I come back? Well, voilà. So in Haro 2, you have three nodes, okay? Okay. And node C is a strong Lyman alpha emitter. Node B is has some dust, but this one a lot of dust. And node A is very ionized, low optical depth. Okay, but the fuse data showing that there is a Lyman continuum from this galaxy. In fact, the aperture encompasses three nodes, so you don't know where it comes from. And when we use HST, we were able to do a proper work on trying to identify where, in fact, we think that the continuum comes from. So we use for that cost data to reveal the origin of Lyman continuum. So we found that in fact the Lyman flux density is shown here for the three nodes. So of course it's very, but you see that the blue one from the node B shows a very good emission. Not A, which is this one, shows no detection. On node B, the node B shows a good detection. Node A as well. But not A doesn't show. On no detection in the green one, detection in the blue on the red one. Okay, and this is when you sum up all these detection, is consistent with the one originally found by Lettet et al. With fuse. But now, of course, we can identify the three nodes one after the other one, and you can calculate the star formation rate. You can measure the escape of the Lyman continuum, which is found to be 4% here. And we also took spectra. You can make the stellar population. You do the same with C. C is this one. And for this one, of course, you expect the detection because there is little dust. And okay, so it's about 6%, and we found 5. Okay. What else? So this is the stellar population. And no detection in the node number 1, node A. And this is because, and this is a funny result, because in fact, if you get a spectrum, it looks very much like a green pea. So oxygen free to ratio is very, very large, and it's about 9. You know? The ratio between oxygen free at 5006 and 3727 is about 9. But we have no Lyman escape. So we believe that if it escapes, it should escape maybe in another direction. Maybe it's collimated. Maybe it is highly isotropic, as it seems to be from the image. Okay, so these are the results here, which are in one table. I have to add that node B and node C are also X-ray emitters. which is an important point. Okay. So if we summarize this, it escapes, of course, if the stellar flux is strong. If it escapes in green peas, maybe it does, but it may be highly anisotropic. And we have to clarify the importance of accretors in the budget, because the ones for which we find the Lyman continuum escape, they show X-ray sources. Now, the last thing I want to briefly discuss is something that appeared in Nature 1 month ago, and ATEC has been the PI of this project, showing why we think now that dwarf galaxies are able to reionize the universe at large redshift. So they were using a field, which is what they have done. This is absolute magnitude of a galaxy, -21, -15. They have observed 7 galaxies, about, between -15 to -70, at redshift between 6 to 9. So, Manuel, is very long, the time where we had we were watching people finding quasars at z of 1, and now we have galaxies at z of 9. Yes, so how they did that? I think these galaxies were found. No, oops. So can I come back to the beginning? No. Yeah, I can run this. So they have been using there is a gravitational lens which is Abel 244, I think. You know this galaxy is huge. Voilà, yes. They use the gravitational cluster lens, Abel 1244, somebody remembers? No? And from them, of course, there is an amplifying factor between 7 to 22. Yeah, you can put again. Thank you. So because of that, it's possible to identify and to discover very, very faint galaxies, okay? And that's the cluster. Inside the cluster, all the encircled objects are very, very faint galaxies, okay? And in fact, I think it's 7 or 8 galaxies they found. They have an absolute magnitude of less than -15, luminosity of 0.005 L star luminosity, and the estimated mass is between log mass to solar mass between 6 to 7. So very, very small galaxy. And then they calculate what they call the ionizing photon production efficiency. Okay, and they measure that. You can see if it's 20% or more. They use first various filters to identify the galaxies, and then, of course, for each one, they use the what's the name? NIRSPEC, which is infrared spectrum on JWST, on using a slitless multi-setting slit, which allows you to repeat the measurements on the same galaxy many times and to avoid to get rid of cosmic rays and so on. And for each object, for one in particular, they get such a spectrum, and you see the Lyman alpha break here, and you can see the emission lines. You can measure then from this spectrum the ionizing photon that escapes, that has been produced. Okay. So at the end, when they have identified the source, they can measure, they know the density of these emitters in this area. And what they found is, so they know how many galaxies you have per cubic megaparsec. And you measure that knowing their intrinsic luminosity. Whoops. Here. So these are the objects, this work. And this plot here, this plot is the two plots, this one in white and this one here, is in fact it's taken from the Schechter luminosity function. And if you want the galaxies to ionize the universe, you should be precisely in this region, okay? If the number density goes down, of course, you are not able to reionize the universe. If you are above this value, about -2, normally models predict that you are able to reionize the universe. Okay? So here, if the field, because it's a very small field, of course, they have been looking at, if this field is representative of large-scale distribution of faint galaxies, then the rate of ionizing photons exceeds that needed for reionization, even if the escape fraction is of the order of 5%, which is, in this case, is even more than what is requested. So the conclusion that they have is this why it has been published in Nature, and why they believe that the main contribution for the reionization is due to dwarf galaxies. Voilà. Thank you very much for.
Thank you. Okay, well, thank you very much for this very nice talk. Question here.
Daniel, that's a lot of work, and I got lost in what's your calibration.
What do you mean calibration?
The calibration between Lyman alpha and the star formation rate. So how good it is,
at some point,
how does it compare with other calibrations?
Well, the Lyman alpha on the star formation rate comes from the fact that we have the spectra.
Yeah, but the calibration, how do you calibrate those?
In what sense? Because we use starburst 99. So we fit the spectrum, the overall spectrum of the galaxy. We can calculate the star formation rate because we know the UV, we know the bulk of the continuum, and we calculate that we're using starburst 99. I am talking about local objects. So we get the star formation rate somehow. We assume, of course, you have to assume it's a burst, or you can compare, is it a burst or extended burst? So we use the best fit. Most of the time it is not extended burst, but it's burst or two bursts. And you compare that with, with Lyman alpha, the H alpha emission, and that's how we get that this result. No, it's not clear? It's not clear. Why? No, because we also have the dust. We have many parameters that allow us to produce this. For these galaxies, which are not for these ones, for the galaxies which are local ones.
Thank you. More questions?
Oui, Sylvia.
Yeah.
a question of ignorance. Now, when you say that the reionization may be due to the dwarf galaxies,
Yeah.
the Lyman alpha from dwarf galaxies, now, where would otherwise have been formed the stars, the stars that produce the reionization? Where else could they have been formed?
There are three possibilities that
that's
people examine. One is that bright galaxies, provided that you have big galaxies, provided that you have enough. And JWST seems to show that even if you see galaxies at after 400 million years, they are not very extremely luminous. They are luminous in the UV, but they are not big galaxies already formed. But this is an hypothesis that some people put forward. The second one is quasars, QSOs.
Okay.
Okay, but
Okay.
one of the problems that we don't see many after
Yes.
it declines very much after z=2. But still, everybody, every galaxy, every population declines after some redshift. So that's why there were some papers showing, arguing that quasars could do the game, right? And but now this is another argument showing that you have enough ionizing density plus enough galaxies for a given volume. That's his argument.
But then, if these dwarf galaxies are the responsible for the reionization,
Yeah.
then you can set up a limit of density and mass and whatever. For
Yes,
these
I think
objects.
I have not. I have here the paper. I can give it to you. I think I'm not sure that I suppose they give this data because.
Because then you need a density.
Yeah, I suppose they give a density, how many objects do you need per cubic volume, but they do that in the last, they use the Schechter function, you know,
Okay.
which gives exactly that, what you are asking. Here. You see that if you have, okay, 10 to minus 1, 10 to minus 1, the density,
Okay.
per megaparsec, cubic megaparsec of the magnitude between being 16 with the ionizing density that they claim to have observed, that's enough to reionize. And something that wasn't obvious because many people thought that at this, in this region, very hard, of course, to obtain the Schechter function at this level. Okay, these works seem to indicate that we are not in this regime, but we are in this regime. But again, they are cautious enough to say that it's a small region, and we are not sure. You know, it's could be a Manquist bias or something.
Okay, thank you.
Thank you very much. Someone in Zoom has a question. You can just speak up.
I wanted to ask you about your sample. Did you detect Lyman alpha in all of the galaxies that the dwarf galaxies that you showed us? Because, and that's one question. And the
Which
other
sample?
one,
You are talking about the large sample?
no, the larger sample, the 45.
Yeah.
And
45.
also, in some of them, there is a very prominent emission in Lyman alpha.
Yes, yes, sure.
And in some of them, it's very
That's
small.
right. That's right.
What is the cause of the difference? Do you know what is the cause of the difference?
The cause is multi-parameter. And I have not shown the plots here because I want you to go back to we have published 14 papers on this subject, but we have done, I think paper number, I don't know which one, where we plot the parameters against each other, dust, color, ellipticity, roundness, and so on. And we have some indications. It's very trivial at some point. After a lot of effort, we find something that you could have thought before. But things like porosity is one. Okay, if you have a lot of dust on static gas, a lot of gas, it will not escape. But if you can have holes, the hole is of course one parameter. Ionization parameters is also one. Fully ionized, density bounded, then of course you have but it's a very frustrating one because I have shown you have two galaxies that look the same. On one you have Lyman alpha, not the other one. And you are at large redshift, so there is no way to identify any of the parameters we are talking about. So this game was an example of the fact that it's not astronomy anymore, it's physics, right? And to do prediction at very large redshift, it's rather complicated. And what you have is only statistical effects. So you can statistical occurrence, but you can if you have one object, you cannot tell in advance what would be the outcome. That's my conclusion.
Thank you very much.
At what Z do you need them to be to
At
have
what?
at what redshift?
Yeah.
Do you need them to have taken place so that they could produce the reionization? Because you have objects that are at 6, redshift of 6.
Yeah.
But are those the earliest ones that they need to be there for the reionization, or do you need much earlier ones than those?
No, I think, well, reionization is supposed to occur at that time. So that's why we're looking at galaxies at that time. They have not found galaxies at larger redshift, but at this epoch,
okay,
these galaxies are enough to reionize at this very epoch.
At this epoch,
Yeah.
okay. We don't need to go further back, further earlier, any earlier, not necessary.
We don't think so, but maybe there will be already some reionization, but the bulk of reionization seems to be already at this redshift between 6 and 7. That's what is found. But I'm sure that JWST will produce more result on this. This is only very primitive. I mean, the first one.
Thank you. Thank you.
Thank you very much. More questions here in the auditorium? If not, let's thanks again for the speaker.
Muy bien.